Welcome. Today, we'll tackle problem number 68, text justification. This is an interesting problem that requires aligning text into neatly justified lines, a task frequently encountered in text formatting systems. Let's dive in and explore different approaches to solve this problem. In this problem, we are tasked with formatting a given list of words into lines of text, where each line has a fixed width specified by max width. The goal is to ensure that each line is fully justified, meaning the text is aligned both to the left and the right. To achieve this, we need to pack as many words as possible into each line, and then distribute extra spaces between the words. If the number of spaces cannot be distributed evenly, the extra spaces should be allocated to the leftmost gaps. For the final line, it should only be left justified, with no extra spaces inserted between words, and any remaining space is padded at the end of the line. The input consists of a list of strings called words and an integer max width, and the output is a list of strings where each string represents a fully justified line of text. Let's look at an example. If the input is words equals, this is an example of text justification. And max width equals 16, the output will be, this is an example of text justification. Here's how this works. In the first line, we fit the words this is and an. There are 3 words and 5 spaces to distribute. Each gap gets 2 spaces, and the remaining 1 space is added to the leftmost gap. The second line contains example, of, and text, and since there is only 1 space to distribute, it is placed between example and of. Finally, the last line contains justification, and since it is the last line, it is left justified, with any remaining space padded at the end. Here's another example. If the input is words equals, what, must, be, acknowledgement, shall, be, with max width equals 16, the output will be, what must be, acknowledgement, shall be. For the first line, the words what, must, and be are used, and the 6 spaces are distributed evenly so that each gap gets 2 spaces. The second line contains only the word acknowledgement, so it is left justified and padded with spaces at the right to reach the required width. Finally, the third line contains shall be, and since it is the last line, it is also left justified, with spaces added at the end to meet the width requirement. Now consider a larger example with words equals, science is what we understand well enough to explain to a computer, art is everything else we do, and max width equals 20. The output is, science is what we understand well enough to explain to a computer. Art is everything else we do. For the first line, 6 spaces are distributed evenly among 3 gaps, resulting in 2 spaces per gap. The second line has only 1 gap, so all 6 spaces are placed there. The subsequent lines follow similar rules for distributing spaces, while the last line do is left justified with padding on the right to reach the required width. Finally, let's discuss some important constraints and edge cases. Each word in the input list has a length between 1 and 20 characters, and the maximum width max width ranges from 1 to 10,000. The total length of all the words is guaranteed not to exceed max width. For edge cases, if there is only 1 word in the input, it must be left justified and padded with spaces to reach the required width. For example, if words equals word and max width equals 10, the output will be word. Another case is when no extra spacing is needed. If the total length of words in a line equals max width, no additional spaces are added. Lastly, for the last line of text, it should always be left justified, even if there are multiple words, with spaces added only to the end as padding. To solve the text justification problem, we first consider a brute force approach. The intuition here is straightforward. We iterate over the list of words, adding as many as we can to a line while ensuring the total length doesn't exceed the given max width. Once we hit that limit, the spaces between words are adjusted to meet the justification requirement, and we move on to the next line. While this method is simple and easy to understand, it is inefficient because we end up recalculating space distribution repeatedly, and we may need to iterate over the same set of words multiple times. Now, in contrast, the optimized approach introduces a more structured way to handle the problem. It separates the process into 2 distinct steps, line construction and space justification. The key is to pack words greedily into a line until the line length exceeds max width. Then, depending on whether the line is in the middle of the text or the last line, the spaces are distributed differently. For middle lines, we distribute spaces as evenly as possible, with any leftover spaces added to the leftmost gaps. For the last line or lines with only one word, we simply left-align the text by appending spaces at the end. This separation reduces redundant calculations and ensures the solution is both efficient and correct. When exploring alternative approaches, we considered a few other strategies. For instance, a two-pass approach involves first determining where line breaks occur in one pass and then justifying the lines in a second pass. While this method results in a clean implementation, it increases space complexity, which can be a disadvantage for larger inputs. Another alternative we investigated was using dynamic programming to minimize the uneven distribution of spaces between words. However, this approach was deemed unnecessary because the problem is better suited to a greedy packing strategy, as it explicitly calls for justified text within the given constraints. Ultimately, we chose the optimized greedy approach because it strikes the best balance between clarity, efficiency, and correctness. Here's how it works. First, we iterate through the words, packing them into a line until adding another word exceeds the max width. Then, we justify the line based on its type. If it's the last line or contains only one word, we left-align it by adding spaces to the end. For all other lines, we distribute spaces evenly between the words, with any extra spaces added to the leftmost gaps. This process is repeated until all the words are processed, ensuring an efficient solution that meets all the problem's requirements. Every approach comes with trade-offs, so let's compare them to understand why the optimized greedy strategy is the preferred choice. The brute force approach is easy to implement but inefficient due to its repetitive space calculations and multiple iterations over the same words. On the other hand, the optimized greedy approach introduces a clear separation between packing and justification, resulting in lower time complexity, (O(n), where n is the total number of words. This makes it both efficient and easy to follow. The two-pass approach offers a slightly cleaner implementation by separating the line breaking and justification steps completely. However, this comes at the cost of increased space complexity, which can be undesirable for large inputs. Finally, while dynamic programming could theoretically minimize uneven space distribution, it overcomplicates the problem without providing significant benefits, especially since the prompt explicitly requires a greedy approach to packing. By focusing on simplicity and efficiency, the optimized greedy approach achieves (O(n) time complexity with minimal space overhead, making it the ideal solution for this problem. Let's start by understanding the problem. You're given an array of words and a maximum width, max width. The goal is to format the text so that each line is exactly max width characters and fully justified. This means the words on each line should be packed as closely as possible, with spaces distributed evenly between words. If there are leftover spaces that can't be evenly distributed, those extra spaces should go between the leftmost words. For the last line, special rules apply. It should be left justified, with no extra spaces inserted between words. To tackle this, we'll break the solution down into key steps. First, we initialize some variables, a result list to store the formatted lines, current_line list to keep track of the words we're working on for the current line, and a variable current_length to track the total length of words in the current line, excluding spaces. This setup ensures we have everything we need to start processing the words efficiently. Now, we move on to iterating through the words. For each word in the array, we check if adding it to the current_line along with at least one space between words would make the line exceed max width. Specifically, we calculate if current_length plus len, current_line plus len, word, exceeds max width. If it does, it means the current line is full, so we call a helper function to justify the line. This involves distributing spaces evenly between words or left justifying it if it's a single word line. Once the line is justified, we append it to the result, then reset current_line and current_length to start processing the next line. If adding the word doesn't exceed max width, we simply add the word to current_line and update current_length. This ensures each line is filled as much as possible before justification. The process of justifying a full line is particularly important. We calculate how many spaces are needed to fill the line using spaces_needed equals max width, current_length. If the line contains only one word, we left justify it by appending all the remaining spaces to the end. Otherwise, we distribute the spaces evenly between words. To do this, we calculate the minimum number of spaces per gap using division and determine how many gaps get extra spaces using the modulus operator. Finally, we construct the line by combining words and spaces step by step, ensuring the correct distribution. The fully justified line is then added to result. Once we've processed all the words, the last step is to handle the final line. The last line has a unique requirement: it should be left justified. To achieve this, we join the words in current underscore line using a single space and append enough trailing spaces to make the total length equal to max width. This ensures the last line meets the formatting requirements. After justifying the last line, we append it to the result. At this point, all lines have been processed and justified. Finally, we return the result list, which contains all the justified lines, formatted exactly as required. There are a few key insights to discuss. First, the crux of the problem lies in distributing spaces evenly between words. By using division and modulus, we ensure that any extra spaces are allocated to the leftmost gaps, as specified in the problem. Second, the last line is an exception. It only requires left justification, with words separated by a single space and trailing spaces added to meet max width. Lastly, it's important to consider certain edge cases. These include handling a single word that perfectly fits a line, words that span multiple lines without needing extra spaces, and lines with varying word lengths that require precise space distribution. To implement this algorithm, we rely on a few key data structures. The result list stores the final justified lines, while the current underscore line list temporarily holds words for the line being processed. Additionally, integer variables like current underscore length and spaces underscore needed help track the word lengths and spaces required for justification, enabling efficient calculations. Finally, let's analyze the complexity of the algorithm. The time complexity is O(n), where n is the total number of words. Each word is processed exactly once, and operations like joining words or calculating spaces are performed in constant time relative to the line length. The space complexity is also O(n), as we store the final result and maintain a temporary list for the current line. To illustrate how this works, consider an example where the input words are: this is an example of text justification, and max width is 16. The output would be 3 lines: this is an example of text and justification. The first line contains evenly distributed spaces, the second line has slightly fewer spaces, and the last line is left justified with trailing spaces. This example demonstrates how the algorithm handles various cases, distributing spaces evenly, managing varying word lengths, and applying special rules for the last line. This Python implementation solves LeetCode problem number 68, text justification, by formatting a list of words into fully justified lines of a specified width. The function fullJustify takes the input list of words and the maximum line width. It initializes an empty list for storing the final result, as well as variables current underscore line and current underscore line underscore length to track the words and length of the current line being built. The algorithm iterates through the words, checking if adding the next word would exceed the maximum width. If so, it justifies the current line by calculating the number of spaces needed and distributing them evenly between the words. If there is only one word in the line, the spaces are added at the end. The justified line is then added to the result, and new variables are reset for the next line. The last line is treated separately, as it should be left justified. The words are joined with single spaces, and the entire line is padded with spaces to the right to match the maximum width. The result is returned as a list of justified lines. This approach ensures that all edge cases, including single word lines and uneven space distribution, are correctly handled. The solution is efficient with a time complexity of O(n), where n is the number of words, as each word is processed once. Here, we start by defining our Java method fullJustify that takes an array of words and an integer max width, which represents the maximum width of each line. We initialize a result list to store the final justified text, a current line list to hold words for the line we are building, and a current line length variable to track the total length of words in the current line. Then, we iterate through each word in the input array. For each word, we check if adding it to the current line, along with the necessary spaces, would exceed the maximum width. If it does, we need to justify the current line. To do this, we calculate the number of spaces to add by subtracting the total word length from max width. These spaces are distributed evenly between the words in the line. If there's only one word, the spaces are added to its end. After the spaces are distributed, the line is joined into a string and added to the result list. We then reset the current line and current line length for the next iteration. If the word fits, we add it to the current line and update the line's total length. Once the loop has processed all the words, we still need to handle the last line. This line is left justified, meaning the words are spaced normally, and any remaining space is added to the end. To achieve this, we join the words in the current line with a single space and store the result in a string builder. Then, as long as the line's length is less than max width, we append extra spaces to the end. Finally, this last line is added to the result list. The method then returns the result, which contains all the fully justified lines of text. To solve the problem of text justification, let's start by breaking down a basic example. The input consists of a list of words and a maximum line width. In this case, the words are, "This is an example of text justification," and the max width is 16. We begin by initializing three variables: result to store the final justified lines, current_line to hold words for the current line, and current_line_length to track the total length of words in the current line without spaces. Now, processing starts with the first word, "this." Adding it to the current line doesn't exceed the max width, so we update current_line to "this" and current_line_length to 4. Next, the second word, is added. This also fits within the limit, so we update the current_line to "this is" and current_line_length to 6. Continuing with the third word, and, we check if adding it exceeds max width. It does not, so we update current_line to "this is" and current_line_length to 8. Now, adding the fourth word, example, would exceed the maximum width, so we justify the current line. The total spaces needed are calculated as max width minus current_line_length, which is 8. These spaces are distributed evenly between the words, resulting in the line "this is an." This line is added to the result, and we reset current_line to example and current_line_length to 7. The process is repeated for the remaining words of text and justification. The final line is left justified because it's the last line, resulting in of text. The final output for this example is an array of lines. This is an example of text justification. Now let's consider a case with a single long word. The input is supercalifragilisticexpialidocious, with a max width of 16. Here, we initialize the same variables as before: result, current_line, and current_line_length. When we attempt to process the word, it's clear that the word itself exceeds the max width. Since we cannot split the word or fit it into a line, it is directly appended as a single justified line. The result becomes supercalifragilisticexpialidocious. Notice how the solution handles this edge case gracefully by immediately appending the word as is. The final output is simply supercalifragilisticexpialidocious. In the next example, we have a shorter input with words, "hello, world," and a max width of 11. Again, we start with the usual initialization of result, current_line, and current_line_length. As we process the words, we see that adding both hello and world together fits within the max width. Since this is the last line, it is left justified, meaning spaces are added only at the end to reach the required width. The resulting line is "hello world," which is then added to result. The final output is simply "hello world," demonstrating how the solution handles fully fitting words in a single line. These examples illustrate how the text justification solution handles a variety of scenarios. From the basic case of distributing spaces evenly, to handling a single long word that exceeds the width, and finally processing shorter lines that require left justification, the approach adapts to different inputs effectively. By carefully managing lines, calculating spaces, and applying justification rules, the solution ensures that the output is correctly formatted for each case. The time complexity of the full justify function can be understood by analyzing the key operations it performs. First, the algorithm iterates through the list of words only once during its main loop. If there are n words in the list, this contributes a time complexity of O(n). Next, for each line that the algorithm processes, it calculates the total length of the words, distributes spaces, and joins the words together. In the worst-case scenario, where max width is very small, each word might occupy its own line, leading to up to n lines. The space distribution for each line involves appending spaces to words based on modular arithmetic. Since the number of spaces is proportional to max width, the total cost of space distribution across all lines in this worst case is n asterisk max width. These two steps give us the foundation for the overall time complexity calculation. The next significant operation in the algorithm is joining the words in a line to create the justified text. The .join, current_line, operation has a time complexity of k for each line, where k is the number of characters in that line, including spaces. When we account for all lines, the total number of characters processed is proportional to the sum of the lengths of all words and spaces, which is bounded by n asterisk max width. This makes the contribution of the joining operation also n asterisk max width. Combining all these factors, the overall time complexity of the algorithm is n plus n asterisk max width, which simplifies to n asterisk max width in the worst case. Now, looking at space complexity, the main contributor is the result list, which stores the justified lines. Each line has at most max width characters, and the total number of lines is proportional to n, leading to a space complexity of n asterisk max width for this storage. The algorithm also uses a temporary current_line list to store the words for the line currently being processed. The size of this list is bounded by the number of words that can fit within max width, so it contributes max width to the space complexity. Additionally, a few integer variables like current_line_length and spaces_to_add are used to track intermediate states during processing. These variables require constant space, or O1. Therefore, the overall space complexity is dominated by the storage required for the result list, which is n asterisk max width. To put this into perspective, a brute force approach might try all possible combinations of words that fit within max width, resulting in an exponential time complexity of 2 to the power of n. The current algorithm avoids such inefficiencies by processing one line at a time and distributing spaces in place, achieving a much more efficient n asterisk max width time complexity while keeping space usage minimal. In terms of best, average, and worst case scenarios, the algorithm demonstrates varying performance based on the input. In the best case, all words fit perfectly into lines without requiring additional space distribution, leading to a time complexity of n. In the average case, some space distribution is required, and most lines are partially filled, resulting in a time complexity of n asterisk max width. The worst case scenario occurs when each word must occupy its own line, such as when max width is very small. Here, the time complexity is also n asterisk max width, with space distribution and joining operations dominating the cost. This behavior can be mathematically explained by the nested operations. Iterating through words contributes n, while space distribution across all lines adds n asterisk max width. Together, these give the overall time complexity of n asterisk max width. Similarly, the space complexity is dominated by the justified lines stored in the result list, which scales as n asterisk max width. When tackling the text justification problem, there are some common pitfalls to be mindful of. One of the most frequent mistakes is failing to handle edge cases. These include scenarios like a single word input, words longer than the maximum allowed width, or even an empty word list. Addressing these ensures your solution is robust, which is critical in interviews where such scenarios are often used to test your thoroughness. Another common issue is improperly distributing extra spaces between words. It's easy to make mistakes that result in uneven spacing or failing to left align the last line as required. This is important because maintaining the correct formatting rules is a key part of the problem. Modifying the input array directly is another mistake to avoid. If you change the words array while iterating, it can lead to unpredictable behavior or errors. Always maintain the integrity of the input unless explicitly told otherwise. Lastly, overcomplicating space calculations can introduce unnecessary bugs. Simpler, more readable logic is not only easier to debug but also makes your solution more elegant and efficient. Another mistake to avoid is neglecting performance optimization. For example, relying on nested loops or recalculating the same values repeatedly can degrade performance, especially with larger inputs. Instead, aim for a solution that processes each line as efficiently as possible. Now, let's focus on some key insights for interviews. This problem is well suited to greedy algorithms, where you process one line at a time, packing words and distributing spaces appropriately. Brute force can be helpful to clarify your logic, particularly for small datasets. However, it's not practical for larger constraints, where efficiency becomes crucial. Always discuss edge cases during an interview. For example, explain how you handle a single word exceeding the maximum width or ensure the last line is left aligned. When distributing spaces, techniques like integer division and modulus, e.g., using divmod, can simplify calculations. Finally, aim for a time complexity of O(n), where n is the total number of characters, ensuring your solution handles larger inputs efficiently. To deepen your understanding of this problem, it's helpful to explore related challenges. Of course, the primary focus is LeetCode 68, which addresses text justification directly. However, other problems like LeetCode 140, Word Break 2, involve string formatting and recursive backtracking, which can help build a broader skill set. LeetCode 127, Word Ladder, emphasizes efficient string handling, while LeetCode 76, Minimum Window Substring, focuses on substring manipulation and optimization. These problems share overlapping ideas and can reinforce your understanding of string-based algorithms. Now, let's briefly discuss alternative approaches. A greedy algorithm is the most common solution for this problem. Using a two-pointer technique, you can pack words into lines and distribute spaces in a greedy manner based on the remaining width. While this method is efficient for most cases, you may need additional logic to handle edge cases. Another option is dynamic programming. Here, you define a cost function for line breaks, such as minimizing extra spaces, and build a solution that optimizes this cost. However, dynamic programming is often more complex and may be unnecessary unless the problem explicitly calls for it. Finally, let's touch on recursive backtracking as another potential approach. This method involves exploring all possible line breaks recursively and selecting the best outcome based on the problem's requirements. While it can be a helpful way to understand the problem's structure or clarify your logic, it's usually impractical due to its exponential time complexity. Recursive backtracking is typically reserved for smaller inputs or conceptual exploration rather than real-world implementation. In summary, while there are several ways to approach text justification, the key is to balance simplicity, efficiency, and correctness to address both the problem constraints and edge cases effectively. Great work! We've reached the end of problem number 68, text justification. Today, we explored how to format text into justified lines using a brute force approach. Remember to practice string manipulation and consider edge cases in similar problems. Thanks for watching, and don't forget to like, subscribe, and stay tuned for more coding solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!